All right, so we should be good to go. So the first thing I want to point out about mass spectrometry is it's spectrometry, not spectroscopy, because it actually has nothing to do with electromagnetic radiation. The spectrum that you're getting in mass spectrometry is intensity on one scale, and that intensity is usually in what we call TIC, which is total ion count. And then on this scale is the mass over charge ratio. And usually for simple molecules like we're working with, Z is +1. So the mass that you're getting is actually the mass of the fragment. When you're talking about larger molecules like proteins or nucleic acids, there might be +2 or +3 ions, and so your mass over charge ratio might not give you the actual mass of the fragment. It might give you a third of the mass or a half of the mass of the fragment. But for our purposes, we can usually assume that the mass that we're seeing on this spectrum is in fact the mass of the fragment. So a couple of other definitions. M+, that capital M+, is what we call the molecular ion. That's the entire molecular weight of the substance. So it's just a molecule that's had lost an electron and been converted into a positively charged species. And in these cases, because of the chlorine, we also have what we call an M+2 because of the other isotope of chlorine, right? 37 chlorine versus 35 chlorine. And we see that M+2 in about a 3-to-1 ratio because 37 chlorine is about a third the natural abundance of 35 chlorine. So we see an M and M+2. That's pretty distinctive for chlorine. When we see an M+ and an M+2 that are in about a 1-to-1 ratio, that's very distinctive for bromine, because bromine has two isotopes, 79 bromine and 81 bromine. And those are usually in a 1-to-1 ratio, which means we see M and M+2 in equal intensities. And then actually for sulfur, because sulfur 34 is about 4% natural abundance, we'll also see an M+2 peak, but it'll be significantly smaller. So the molecular ion region of the spectrum is a region you can look at to determine what heteroatoms might be present, chlorine, bromine, sulfur, things like that. And then the other definition is what we call the base peak. And that's the one we set to 100%. So with our total intensity, we're not actually measuring the total ion count here. We're measuring a ratio of the total ion count for the fragment to the total ion count for the base peak. So this is often in percent, where 100% is the most abundant peak. If you look at the data, the data will give you numbers in total ion count, and they'll be huge. They'll be in the 10 millions, sometimes 100 million range. So we just basically calibrate that to 100%. So when you look at the numbers in parentheses, if you're looking at a mass spectrum from the literature, those number in parentheses are the percentage of the individual fragment relative to the base peak set equal to 100. So in the table, right, that you saw with retention times and percent area, that last column told you what the base peak was, right? So peak number, peak 1, right? Peak 1, 2, 3, and you had 7 peaks, right? Because we managed to separate 7 of the 8 isomers. So this base peak, I think you noticed, what's the base peak on pretty much all of them except for 1? Have you had a chance to look at the data yet?
81.
It's 81 for all of them except for?
The 83 on the 7th peak.
On the 7th peak is 83, right? So it's almost always 81, but we didn't tell you anything about where that 81 peak came from, right? Why is 81 the abundant peak? We did tell you what to look for, right, this 83 peak, right? Because that's loss of CH2Cl. And from the molecular ion, that would be 35 plus 14, right, which is M minus 49. Am I right on that? Yep, because the molecular ion is at 132 for our molecule. All right. So M minus 49 is loss of this CH2Cl fragment as a radical. So what happens when we do a mass spec? There are various types of mass spectrometry, but the type we're doing is called EI. That stands for electron impact. Fetch a different pen here. Hopefully I didn't mess up the camera too much. Right? So electron impact. So what we have is we have a gold filament. We have a vacuum chamber. And on the other side we have another gold filament. And we introduce our sample. Let's take the 2-chloro derivative just as the example. We introduce our sample into that vacuum chamber with a little bit of helium, right, with the helium gas, which is the carrier gas for the GC. But it's very low pressure. There's hardly any stuff in there. And we set these to be at a potential difference of 70 electron volts. Right? So that's a large potential difference between these two fragments. There'll be a negatively charged and a positively charged filament. And as we build up charge on here, these electrons are going to sit on the surface. And eventually you'll have built up such a large energy difference across that one of these electrons is going to shoot across. And sometimes it hits one of the electrons that's in the molecule. And when it does that, both of those electrons, right, the one that went colliding and the one it hit, are both going to go shooting off. And when they collide with this gold filament, we'll see actual charge, right? We'll have the electron flow. And that's what we're seeing with the total ion count. Basically, each one of these electrons that impacts, right? Or, sorry. The total ion count now, we're going to... So we got our gold filaments, and we just bombarded it. If you've ever played marbles, it's very much like marbles, where when the electron hits it, both of them go shooting out. And what we will have done is created an electron deficient species where one of the highest energy electrons, which is often a lone pair, if you have lone pairs in the molecule, generally one of the lone pair electrons is the one that's gone. So what we have here is a radical cation. And that charged particle is now swept by the helium gas onto into what we call a quadrupole mass selective detector. The quadrupole mass selective detector is a series of metal rods that are a certain length, and the degree of separating power depends on the length of the rods. So what we're doing is we're sweeping our sample into that space between the rods, and we're adjusting the charge on these so that the sample, as it starts getting attracted to the negatively charged rod, won't quite hit it, and then we'll switch, right? We rapidly switch these charges. So that if the thing has the right mass over charge ratio, it will be kept in that chamber and it will come out and hit the detector. If it's too heavy, right? If it's too heavy, it's going to build up too much momentum, and then when we switch the charges, it's not going to be able to stop, and it's going to go colliding with the negatively charged rod and not hit the detector. If it's too light, then when we switch the charges, the amount of energy or the amount of force exerted by those charged rods is going to be too much, and it's going to push it further than it should. So what we see is we see a helical path here where only the molecules with the right mass over charge ratio can make it all the way through to the end and hit the detector without colliding with one of these rods. It's a relatively low resolution mass spectrometry technique, this kind of quadrupole that we're looking at. It's not the one you would have seen in your textbook for general chemistry, which is a more expensive instrument. But the GC mass spec with this quadrupole detector only costs about $70,000, and a full-on mass spec of the type that you see in the Gen Chem text costs $500,000. So obviously we can't afford that. So we've got this quadrupole detector. It's only accurate to about plus or minus 0.6 atomic mass units. Right? So we're not able to do exact masses. We can't tell the difference between CH2, which has a formula mass of 14, and nitrogen, which has a formula mass of 14. But on the more sensitive instruments you can, because CH2 and nitrogen are both 14, but they differ in the third and fourth decimal place. So what happens is that radical cation, though, is not very stable. You know that radicals tend to be unstable. So in most cases, that radical cation is not going to make it through the quadrupole intact. It's going to start falling apart. Okay? There are two types of fragmentation that can occur. One is called alpha cleavage. And what that is a homolytic cleavage of a bond in the molecule. And it yields a radical, which is neutral and therefore invisible. And a carbocation, which is detected. Homolytic bond cleavage means one electron goes each way, so we can cleave any, in theory, right, any of these bonds. One of the things you might do is cleave this group. So one of those electrons would go with the CH3, and the other electron would end up here. I'm going to draw the hydrogens in here just so we see them. Right? And so the fragment would release a methyl group, which has a molecular weight of 15. And then it would produce this radical. There's a positive charge there. We might expect this loss of methyl. So we're going to see an M-15 peak. That'll be at M over Z 117. We might expect this loss of methyl to be pretty favorable for the 2-chloro derivative, because now these two electrons can join with each other, and you could end up with a cyclic chloronium ion, which is similar to what you've seen, right, when you're adding halogens across a carbon-carbon pi bond. So that chloronium ion should be fairly favorable, and this M-15 peak might be more prominent for the 2-chloro derivative than it would be for some of the other ones, where these radicals would now be further away and not able to combine. So that's alpha cleavage, right? And because chlorine is polarizable, loss of chlorine is a fairly common fragmentation, and that's the one you saw, I think, in figure 5 in the lab manual, where the chlorine actually took its electrons with it to form a carbocation and a chlorine radical. So in that case, what you'd be looking at, actually, the loss of chlorine, you'd be looking at the chlorine taking both of these electrons with it to leave a carbocation that looks like this, and chlorine radical. And you'd see that as M-35 for loss of chlorine, right? So that's the peak that you would expect to see at M over Z 97. And the more stable this carbocation, the more likely it should be to happen. So it should happen more if the chlorine was on the tertiary position. But you might expect for the secondary one, you'd see a decent sized peak at M over Z 97, because you can get a hydride shift, right? If you do a hydride shift, then you can still get the more stable tertiary carbocation from the original fragmentation. So you saw that there are two peaks that had a 97 peak that was bigger than the 96 peak. Which two peaks had the 97 peak bigger than the 96 peak? There were two of the 7 molecules.
First and second peak.
All right, so that was peak 1 and peak 2. One of those is probably the tertiary chloride, and the other is probably one of the secondaries, one of the 2 chloroderivatives. The third peak that you see in the GC mass spec, peak 3, is 2 things on top of each other. That's why it's a little bit bigger than the others. My guess is it's the other 2 chloroisomer, and then probably either one of the 3 or one of the 4 chloroisomers, but it's a little hard to tell. So the second pathway for fragmentation is called a rearrangement. And it's distinct from an alpha cleavage in that it loses a neutral molecule and generates a new radical cation. And then that radical cation can undergo further fragmentation. So you'll actually see the kind of parent fragment from the loss of this neutral molecule, and then you'll see daughter fragments where the new radical cation is fragmenting again. And a common pathway is loss of HCl. If it's water, a very common pathway is loss of H2O, which would be M-18. So a loss of HCl you should see at M-36 at M over Z 96. And you see that 96 fragment, in theory, you can see that 96 fragment from any of the isomers, because the loss of HCl can happen for any of them. So how does that work? Well, you've got the same radical cation that you would have before, our CH3 over here. So what can happen is this chlorine can grab an adjacent hydrogen, right, to form the neutral HCl, and that would then put this other electron down here. These 2 electrons are going to go with the chlorine, so what you form is hydrogen chloride, and then you form a new radical cation, and that new radical cation looks like this. It's basically a pi bond with just 1 electron. And you could write it with the positive charge on this carbon and the radical on that one, or the other way around with the positive charge on this carbon and the radical on that one. And then that can fragment again. So the question is, how might that fragment if what you had was this? Right. So this is the thing that has the M over Z equals 96, but then it can pretty readily lose the methyl group. One of those electrons will now form a new pi bond, and the other electron will go with the methyl group. So we'll form CH3 radical, and we will form a cation that's actually resonance stabilized. This is what we call an allylic cation. And you can write a resonance structure that puts the positive charge on the other end as well. And the double bond in a different position. So that's stable, relatively speaking. So you might expect that after the loss of HCl from the 3-chloro derivative, you can lose methyl. This will now be at 15 less, right? So this will be m over z 96 minus 15. Well, that's the m over z 81 peak that you're seeing. And that's a fairly prominent peak for all of them that have a CH3 group at all, right? So when you see m over z 81, what you're seeing is m minus 36 for the HCl minus 15 for the methyl. You can't do that if there wasn't a CH3 group in the first place, right? If you had a primary chloride, the only possible primary chloride, it could lose HCl, right? You would expect it to be able to take this hydrogen off and form the radical cation that looks like that, plus HCl. So you ought to see m over z equal 96 for the primary, but you then can't lose CH3 because there is no CH3 group, so m over z 81 isn't possible. And that's what you saw for the 7th peak, right? So the absence of the m over z 81 peak is also diagnostic for the primary, in addition to the presence of the m over z 83 peak. Right, that m over z 83 peak, I think we told you where that came from, right? Did we, was that figure 4 in the lab manual? That showed you what that looked like? Maybe, yes? Right, so we're losing the chlorine. The chlorine is going to fall off along with the CH2 group. So this pair of electrons is going to come out, and what we're going to form is the CH2Cl as a radical cation, and then, sorry, as a radical, not a radical cation. And then the carbocation that we're seeing is this, and that's the m over z equals 83 peak. Chlorine can expand the octet, so it can stabilize the missing pair of electrons on the carbon. And I should have 7 there, right? So the radical, that's invisible. So the fact that we see this peak and we can't see the loss of methyl, right? That's pretty distinctive for the primary. So which peak was the primary? Emma, I think you already figured it out, didn't you? You may be the only one that's actually looked at the data yet. So,
yeah, I got that peak 7 was primary.
Right. So in your notebook and in your report, you're going to want to use the mass spec as your method for identifying which is the primary. But then if you look at the boiling points, I think it's also consistent with the boiling points, right? You can't use the boiling points distinctively for all of them because you only have the boiling point for 3 substances. But I think you saw that the primary had the highest boiling point, which would also be consistent with it having the longest retention time. So peak 7 is almost certainly the primary. Peaks 1 and 2 both have a fairly prominent 97 peak. Which one of those has the more prominent, or the, in which one of those is the 97 to 81 ratio the largest? Do you understand what I'm asking?
The first one.
Right, so that's peak 1. Right, so what we're looking at when we see that 97 over 81 ratio is we're looking at 97, which is loss of chlorine radical to form a carbocation. And at 96, we're seeing loss of HCl to form a radical cation. And then that 96 peak is generating the daughter fragment at AC1 with loss of CH3. So if loss of chlorine is pretty favorable, you'd expect loss of HCl to be relatively less favorable. Once you've lost the HCl, it's pretty common to lose that methyl group. So if you lose chlorine, that's a terminal pathway, right? It can't go any further because we've generated a carbocation that's not subject to further rearrangement. If you lose HCl, that's not a terminal pathway. We can then lose the methyl to form the 81. So the one that has the largest 97/81 ratio is the one that loses chlorine the most readily. And which one should lose the chlorine most readily? I think when I was emailing with you yesterday, Emma, I was telling you should look at the 97/96 ratio, and that's not what I meant. It's the 97/81 ratio that allows you to distinguish between the tertiary and the secondary. Because both tertiary and secondary can lose HCl to form 96, but the secondary is going to generate a lot more of the 96 over the 97, which means the secondary will generate a lot more 81, right? We should see a more prominent 81 peak for secondary chlorides. Which one had the lowest boiling point?
The tertiary?
Yep. So again, it's consistent, right? The shortest retention time is also consistent, not only with the larger 97/81 ratio, the prominent loss of Cl radical, but also the lowest boiling point would predict. So now you know which peaks are which, right? Peak 1, that's tertiary. Peaks 2 through 6 are all secondary. Peak 7 is primary. What are we going to do with that data? I know Dr. Thomas is not particularly into the whole relative reactivities, and so she doesn't usually teach it. I don't know how much time Dr. Pissner spent on relative reactivities. I know I did it. So what is a relative reactivity? What's the equation that allows us to work with how likely an individual hydrogen is to be plucked off by chlorine radical? What were the percentages for peak 1 and peak 7? Do you have those handy? I can look them up, but you might have them right in front of you.
Peak 1 is 6.2.
6.2, peak 1? I don't believe you.
And 7, oh wait, sorry. Peak 1 was 17.4.
Peak 7
And
is
peak
6.2,
7.
right? And
Yeah.
this one was 17.4. And so this was everything that's left? Correct? Isn't that 23.6 total, right? So what's this? $100 minus 23.6, right? What's that? 86.4? 76.4? Question mark? Does that work? Is that what everybody got? Don't all talk at once. Is that what you got, Emma?
I had a question about whether we should consolidate all the area percents for the secondary.
Yes, you should. There's no reason, because you don't know which one's which for the other ones. You don't know, like for the 2-chloro and the 3-chloro, right? There are 4 different hydrogens that could lead to those. But for the 4-chloro, there's only 2 different hydrogens. So you don't know what to divide through by each of those other peaks. The only way to handle it is to treat them all as we're going to make the assumption inaccurate, but close, that all of the secondary hydrogens are equally reactive. Probably not quite true, but we're just going to lump them together.
It is
Okay, yeah, I got
76.4.
Yeah, I thought I could do that math in my head. Right, so the observed percentage for the tertiary is 17.4, for the secondary is 76.4, for the primary is 6.2. That makes it look like the primary is the least reactive, but it doesn't make it look like the tertiary is the most reactive. So what do we have to do in order to compare the relative reactivities? We can't just use the observed percent. There's an equation that has to be rearranged. The only significant peaks in any of the mass spec were, right, the loss of methyl at 117, the loss of HCl at 96, the loss of chlorine at 97, and then the peaks at 81 and 83. The rest of the stuff at 55, that's the ring falling apart and giving weird shit. You always see peaks at 55. So those aren't really something that you would ever need to look at in diagnosing the spectra. But I did want to tell you where all the major peaks came from, especially since the base peak is one we didn't tell you about in the lab manual. We'll cover mass spec a lot more detail in the second semester course. So what am I going to do with these numbers? Who's in my section? Most of you. What was the equation that related observed percentage to relative reactivities? It was on exam 1.
Divide by the hydrogen.
The what?
The hydrogens.
What about them?
Like the possible hydrogens that could react with it.
Right, so that's the statistical distribution. Statistical factor. So the equation is that the observed percent is equal to the product of the statistical factor. Right, how many hydrogens there are that it could collide with. Times the relative reactivity, which tells you how likely each hydrogen is to react. Obviously, we have the observed percent, right? That's the information we're getting from the GC mass spec. This is what we're looking for. So we need to rearrange that equation to solve for relative reactivity. So what's the relative reactivity equal to? You're just rearranging A equals B times C and solving for C, which I hope is a trivial thing. If it's not trivial, then you're probably in the wrong class. Maybe even the wrong field of study entirely.
The observed percent divided by the
Observed percent divided by the stat factor. Right, so for the tertiary, it's 17.4, and how many tertiary hydrogens are there? So then be a good time to write the molecule out with all the hydrogens attached. So you make sure you count correctly. There's a total of 14 hydrogens, right? Because this is C7 and it has 1 degree of unsaturation. So it should be C7H14. Hopefully I drew 14 hydrogens. So how many tertiary hydrogens are there?
1.
You guys are sleepy today. So just 1. For the secondary, how many secondary hydrogens are there? We're going to take that 76.4.
10.
There's 5 CH2 groups, so 10 total. And for the tertiary, we're going to take that, sorry, for the primary, we're going to take that 6.2. And how many primary hydrogens are there?
3.
Must be what's left, right? It's got to add up to 14. So the squares are the primary hydrogens, the triangles are the tertiary, and the circles are the secondary in my little picture. So we're going to divide through by 3. It's really common to switch those two numbers. People are often switching those two numbers because peak 1 is here, and you really want peak 1 to be primary because they both have a 1 in them. But that would give you the wrong answer, right? This one's trivial. I can do that one in my head. That's 7.64. Right? This is 17.4. And what's 6.2 over 3?
2.06.
2.06. I want to normalize it so that my primary is equal to 1, because in the textbook, right, we see primary to secondary to tertiary. In my book, it's 1 to 4 to 5. What is it in Klein? Someone from Pissner's section want to tell me what the numbers are in Klein for primary, secondary, tertiary? They're different. Anybody? There's 3 of you that could, in theory, answer that question. Actually, I guess there's 2 of you here, Joy and Ankita, because Nalami's not here. Do you have those numbers in your book? No? Did Pissner do relative reactivities at all? Or is this all brand new to you? You awake? This is bringing back bad memories from my class, right? So what do I have to do before I can compare these numbers to these numbers? You haven't covered it. Well, it's a good thing I'm covering it now then. You'll find it in your textbook. The numbers will probably not be 1 to 4 to 5. They'll be in the chapter on radical halogenation. I think it's chapter 13, maybe. The free radical reactions in Klein. So you should use your text, the numbers in Klein, rather than the 1 to 4 to 5, which is from my text. Anybody? What am I going to do with these numbers? What do I have to do to normalize them so I can compare them to the 1 to 4 to 5 ratio? Yes, indeed. Divide through by the smallest one. So normalize by dividing each through by 2.06. So that the primary becomes 1. And then you'll get the other numbers. Right? So your conclusion, obviously, you should go through the calculation of how you get to these normalized numbers, and then you should compare them to the textbook, and then suggest reasons why they are different, because they are. Has anybody gotten the numbers besides Emma? Or is this kind of something you were planning on doing just now? Okay. So when you write your lab report, which is going to be due after break, right, you are going to want to go through a little bit of this reasoning process. You'll want to explain how you identified which peak was which in the GC mass spec. It would be appropriate to have that table of retention times. So we got 8.42 here, and we got 3.69 there for secondary. Right. So, and then you'll want to also use the boiling points with the reference for the boiling points. A lot of you had the bad reference for the boiling point, so you'll want to correct it to the one that I showed you on the grading checklist. So you use the right boiling point, right? For identifying your peaks, it would be appropriate to have the table in there. You don't need to actually show the calculation, right? But you need to explain that the numbers were corrected for the statistical factor. And then once you get these numbers, you're going to need to explain, do they make sense? Are they at least in the right ballpark for where you would expect them? And if they differ, why do they differ? And we gave you two things that could possibly go wrong, the same two things that could possibly have gone wrong for the substitution lab. So what are the two things that could possibly have gone wrong if the person doing this lab wasn't very good? Fortunately, I didn't knock this one over.